So the topic of our today's class is measurements and manipulation of biomolecular ions. So we're going to spend some time talking about mass analyzers in general. We'll consider a couple of them, time of flight and quadrupole filter. And we will also spend some time talking about mass spectrometry. So the reason I wanted to have this discussion of essential nuts and bolts of mass spectrometry, and this is something that I was trying to avoid for the most part when we considered other analytical techniques, is very simple. I already mentioned several times casually resolution, high resolution, low resolution, high accuracy in mass measurements and so forth. And all these notions kind of came out of thin air. So they're not really, we didn't have a chance to see where all these things are coming from. And so I hope today, in today's discussion, and I want to continue that on Friday, we are going to familiarize ourselves with various flavors of mass spectrometry. And so hopefully all these abstract notions of resolution and some other capabilities that I mentioned previously, they would make much more sense to us. So let me start by going to the slide that I have already shown to you at the end of last week. So when we briefly went through the mass measurement process, I mentioned that there are various options available to you. They come at various costs and they offer very different capabilities. And so one of the most important things was instrument resolution. So something that we definitely mentioned. And I wanted to illustrate that with one example on my next slide. So here you see a mass spectrum of a peptide. So the amino acid sequence of this peptide is shown at the top of the slide. And we have actually an overlay of 3 spectra acquired with 3 different instruments. And so they represent 3 different slices of the market, so to speak. So the top spectrum, and I am going to look at the zoom. So we're interested in a +2 charge state. So the top spectrum is acquired with the most generic, the most inexpensive type of instrument, quadrupole mass filter. So we're going to talk about that today towards the end of the class. And here, the resolution is so bad that you cannot even discern the presence of distinct isotopic peaks, right? So you probably can guess that there is something there, but it's not resolved well. And so we just see pretty much a single peak with a convoluted shape. The next trace shown in gray here, this is the mass spectrum acquired with a mid-range instrument. And by mid-range, I understand both the cost category, the expense, as well as the analytical capabilities. And so now you can see that we can clearly determine that this is +2 charge state. We definitely see distinct isotopic peaks, right? But if you really, there is something wrong with this spectrum. And so if I were to calculate the isotopic distribution for this particular peptide, I think last time I gave you a web URL address for a site that I use for calculations that are made based on molecular formulas. When you deal with peptides and proteins, it's much easier not to calculate the empirical formula, but rather deal with the sequences, which you can cut and paste right into the program. And so for that, again, there are a variety of tools available on the web. My favorite is Protein Prospector. So this is an engine which has been developed and is supported continuously by UCSF, Department of Pharmacy. It's been there for at least 20 years. It works really great. It has many capabilities. So this is just one of the things that they can do, calculate the isotopic distribution and masses. As we go through tandem mass spectrometry applications, I will try to show you some other things that you can do with this engine. So it works really great. I highly recommend it. And so here, if you look at the isotopic distribution that is calculated for you based on the amino acid sequence, you see that we definitely have a deviation, a very significant deviation from what we see. Instead of the monotonic decrease in the abundance, we see definitely non-monotonic dependence, right? So, and you can make a guess as to what the reason for that is, but none of these guesses, you would not be able to prove or disprove any of these theories based on this particular instrumentation. So you really need to go for a very high-end instrumentation. And so this last trace here represents the mass spectrum acquired with the so-called ion cyclotron resonance mass spectrometer. So let me label it for you. This is a quadrupole filter. So I put a capital K. This is a time of flight instrument. And this is ion cyclotron resonance, FT-ICR. So FT stands for Fourier transform ion cyclotron resonance MS. So this is highest resolution. Okay, and so these two traces are shown here. And so when you look at the mass spectrum acquired with the top of the line instrument, so this is absolute state-of-the-art instrumentation, which, by the way, we do have here on campus. It's part of the mass spec facility. It's located on the second floor of the LSL building. And so here you see the answer to our question. So what appears to be a single peak acquired with the time of flight instrument, now you can clearly see that it has two contributions, right? So the masses are very close to each other. So you actually see the difference only in the sixth significant figure. And so this is the reason why we need to have this very high resolution in order to be able to see this difference. And so the reason for the presence of this particular peak is fairly mundane. So for those of you who are working with peptides and proteins, know that there is a process, a type of non-enzymatic post-translational modification, which essentially is a degradation of your protein, and it's called deamidation. So what it does, it affects asparagine residues, and it converts asparagine to aspartic acid, right? So that results in the mass increase of 1. So you convert amide to carboxylate. If this degradation product, is present at relatively low abundance, then it would nearly coincide with the +1 isotopic peak of the main peptide, right? And unless you have very high resolution, as in this case is provided by FT-ICRMS, then you would not be able to resolve that. Okay, so this is one of the reasons we need high resolution. So I want to spend next 20-25 minutes talking about ways we actually measure mass to charge ratios in mass spectrometry. And today we're going to cover only 2 analyzers, time of flight and quadrupole MS. Hopefully on Friday, we'll extend our discussion to include the state-of-the-art instrumentation, ion cyclotron resonance mass spec. But I want to start my discussion with just reminding you that in mass spectrometry, the way we can make a distinction between ions of different masses and charges is that we look at their behavior in either electric or magnetic fields. Or we can, in some cases, we use a combination of electric and magnetic fields. Just to remind you, these are basic facts from your high school physics or physics 2 in college. If you place an ion in a uniform electrostatic field, as shown here on this slide, it will not experience any force in the direction orthogonal to the field, right? The force would be parallel to the field. And so let's say if I have an ion that flies into this zone where you have uniform electrostatic field, it will assume parabolic trajectory, right? So it will be accelerated in the vertical direction towards the electrode of the opposite polarity, and its velocity in the horizontal direction is not going to change. So an important thing is that the component of the kinetic energy that would be acquired, so let's say, let's assume initially you have an ion that was resting, velocity 0, and then you place it in the electrostatic field. So the amount of the kinetic energy that would be acquired by this ion would be equal to the product of the total charge of the ion and the potential difference between the 2 points. So the distance that is traversed by your ion, the potential difference between these 2 points is V. So this is how we make these calculations. So this is very simple, almost trivial, and surprisingly, one of the most useful, one of the most common types of mass spectrometers, the so-called time-of-flight mass spectrometer, is using exactly this very simple math. So from here, you can see that you can calculate easily the velocity that has been acquired by your ion based on the potential difference that it went through. So this is how it's used in the time-of-flight mass analyzer. So imagine we have an ion source, and let's say, just for the sake of argument, we have a multi-ion source, right? So we have pulsed ion source, and so all of our ions are produced here at the surface, at the at the surface of the metal target, and then they're accelerated. So there is a potential difference between the point of origin of our ions and this second electrode, and this is the potential difference that all ions are going through. So this is how they accelerated. And upon exiting this region, they would have this velocity. So the velocity of each ion would be uniquely determined by the accelerating potential, V0. So this is something that we can control. And mass to charge ratio of our ion, right? So this is just a very simple mathematical rearrangement of the formula that I had on the previous screen. Now, this drift region is the region where you don't have any field. So this is sometimes called field-free region. And so whatever velocity our ion had at this point, when it was exiting the acceleration region, this velocity will be maintained throughout the entire length of the drift region. Now, ions that have very low M/V ratios, their velocities will be high, right? So remember, velocity is inversely proportional to the square root of M/Z. And heavy ions or ions with fewer charges, they would move much slower. And so this is the physical basis of ion separation. So if we know the distance between this point, entrance to the field-free region, and the detector, and so this is D, capital D is the distance between these 2 points. For each group of ions, I can calculate the time of arrival. So by simply dividing D by the velocity of this ionic group, right? And so that would be the formula. Again, very, very simple. One thing I want to emphasize again, the time of arrival for each group of ion will be determined uniquely by their mass to charge ratio. okay? And so it means that we have the ability to separate ions based on their mass to charge ratios. And you've seen the spectrum already when we discussed molding. So this is how it is produced. So these are two ions of the same mass, but in this case, charge is equal to +1. In this case, charge is equal to +2. And so the arrival times would be different, right? Again, if you had ions of different masses, you would also be able to see that in the mass spectrum. So a very, very simple principle of operation, and it really gives you a lot of advantages. So a very important advantage, and this is the reason why these instruments are so common and so popular, is they have very favorable duty cycle. So the duty cycle is very close to 100%. You're not losing anything, simply because you're not discriminating against ions. You're just separating them, right? And on the ideal circumstances, when you don't have any losses inside the instrument, all of the ions that had been produced in the ionization source, you would be able to detect them, right? So you're not losing anything. And this is very, very important advantage, particularly when it comes to analysis where we need to strain our capabilities and we want to achieve very high sensitivity, very low limits of detection and so forth. This becomes very important. The way I presented this technique to you, I used MALDI as an example, and so you can guess it's ideal for pulsed ionization, right? You use a very short pulse, you produce ions, and then it takes longer time to analyze these ions, to measure their mass to charge ratios. And the process of measurement is completed before you have the next pulse of ionization, right? But you can also apply that to electrospray ionization or some other continuous ionization techniques, as long as you have some modifications to the very simple design I showed in the previous slide, and you introduce some ion storage devices. So you produce ions continuously, and you store them continuously without losing any of them. And then you have an electrical pulse that pushes them into the acceleration region. And so you convert continuous to a pulsed technique, essentially, but you're not losing anything. So you still can take advantage of very favorable duty cycle. And lastly, you can achieve very high mass resolution. There are trade-offs. Usually with time of flight, you can do that for ions with fairly modest M/Z ratios, but you can get to mass resolution up to 10,000. Oh, and it just occurred to me that I never defined mass resolution. Okay, so mass resolution, the way we define it in mass spectrometry, is very different from chromatography. So resolution, you only need to have a single peak to define the resolution. And so resolution would be defined by M/Z ratio of your peak divided by its width at a specific height. So historically, it was 10% of the height. But now, unfortunately, and I have to admit that it was driven primarily by marketing needs. So we always, people who market instruments always want to have to show higher number of values of resolution. And so now we moved up here. So now you report peak width at 50% height. So obviously, without making any changes in the instrument hardware, all of a sudden you have a very significant improvement in resolution, right? So this is why marketing folks like it so much. But so this is unfortunately, this has become a norm, and so this is what we're using now. But this is how you look at resolution. So unlike chromatography, you don't need two peaks. You can define resolution by looking at a single peak. All right. So what are the issues with mass resolution? In this class, we don't have enough time to go through all of this in great detail. Those of you who are interested in mass spectrometry, I suggest that you consider taking a biological mass spectrometry class, which will be offered next semester by my colleague, Professor Richard Vacher in the chemistry department. He is an excellent instructor, and he really goes into very significant depths, trying to explain how things work, and more importantly, why things sometimes do not work. Okay, and so he would be able to give you much more complete coverage. But I will simply mention a few things. So one limitation on the resolution is the temporal dispersion. When we talk about ionization pulses, we assume that the pulse is infinitely narrow. In reality, it is narrow, but it has a finite width, right? And as a result of that, even before you started separating your ions into separate groups, you already have some dispersion within the same group, right? There would be ions that have been generated at the very beginning of your pulse, ions that are generated at the very end, and of course there would be a lot of ions in between. So that would limit your resolution. Space distribution. So ions are not all produced in the same space. So some of them are closer to the exit plate, some of them are further from it, and so that would result in ions having to go through slightly different potential differences. So the voltage, the accelerating voltage that each individual ion would experience would vary slightly. And so that would, of course, be translated into variation in the velocity. Kinetic energy distribution. So when I presented my simplistic diagram, I assumed that ions have zero energy prior to the ionization event, which may not be true, right? And so this extra velocity that they have, which is not related to the acceleration in the electrostatic field, that would also limit the resolution. And finally, we have ion fragmentation. So this is another thing that limits the resolution. So I want to deal with just one of those things, and just to illustrate the ways that we can use to overcome this difficulty. Again, just for illustration purposes, I randomly selected one particular issue. So this is ions having initial velocity distribution, which is not related to the acceleration. So you can imagine when you have this, let's say when you deal with MALDI ionization, you have this laser hitting the surface, it results in ejection of material in the plume. And even before these ions begin to accelerate, they already have some initial velocity, right? And so this initial velocity, we calculate it. Here I present two variations of the formula that I have shown before. So this is the travel time through the drift region for ions that have zero initial velocity. So their velocity is only determined by the acceleration potential. However, if you had some initial velocity, then it would look to you as if you had some extra acceleration potential, right? So that's the result of that, and that would result in a spread. So ions, as you see here, having the same mass, same charge, they would have different arrival times. So this ion that had initial velocity, it would arrive at the detector sooner, right? And so to you, it would appear as if it were ion with a slightly lower M/Z ratio. So how do we deal with that? So unfortunately, if we have a linear time of flight instrument, so this is the top diagram here, this is what we've seen earlier, you really don't have much in terms of capabilities how to deal with this problem. So in order to fix that, you have to have a slightly more expensive instrument. So see, everything comes with a price tag, right? Every useful feature that enhances your capabilities, unfortunately, you have to pay for that. So, but most modern instruments actually have this option, and it's called reflectron. So reflectron is a very nice name because it's self-explanatory. What it means is that you are not making a detection immediately, but instead you place an electrostatic mirror here at the end of the instrument. So this is a region with decelerating potential. And so decelerating potential in absolute terms is actually slightly higher than accelerating potential. And so what it does, it makes your ions to make a U-turn. So let's imagine we have two ions. They have identical MOVZ ratio, but one of them is slightly faster because it had this extra velocity component, some velocity prior to acceleration, and it's shown in gray. So now, by the time they reach reflectron, they are already at different positions. This one on top travels faster, and so it enters reflectron sooner, right? So both of them will make a U-turn inside electron. But this guy shown in the top, because it has higher energy, it would be able to penetrate our electrostatic mirror a little further, right? So it will also make a U-turn, but it's going to take extra time for it to do that, just because it has this extra energy. And so, therefore, when they exit reflectron, it would actually be behind the other ion, which is slower, right? So it sounds like a paradox, but it's not really a paradox. The slow ions spend less time inside reflectron. And so it's cheating in a sense, right? This is why it emerged sooner. And so you can always make calculations and design an instrument in such a way that by the time they reach the detector, these two ions will be in the same plane. So it's like focusing, right? They would still have different velocities. So these ion, it was at the top initially. Now it's at the bottom. It still has high velocity. But for us, it doesn't really matter because what we measure is not the velocity. We measure the arrival time, right? And so that's what it matters. And now instead of having a spread, you will have a collapse in this peak, and you would register both ions at exactly the same time. So that has resulted in a very significant improvement of resolution. So a very, very useful way, very useful piece of hardware. And as I said, most modern time-of-flight instruments are equipped with that. Unfortunately, and I guess I have to put a little sour note here, even though it works great with ions with relatively low MOVZ values, let's say below 2000, sometimes you can extend it up to 3000. Once you go to larger ions, heavy ions like intact proteins, it's not going to work for you, right? So there are many other technical issues that begin to arise. We don't have time to talk about them. I just want to put this mental note that it works great with smaller ions, modest MOVZ values. It doesn't work with larger ones. Okay, so it's not a universal answer. It's just a very useful trick to play with most common types of analytes. When you deal with peptides, for example, this is all you need. Once you go to intact proteins or nucleic acids, forget it. It's not going to work. Okay. But otherwise, again, it's a very popular type of mass analyzers. The price tag, I think I mentioned last time, it's about $500,000, 500,000. So give or take, depending on configuration. And believe me, in the mass spec field, it's not considered to be super expensive. Okay, right. Derek, you look shocked. Now you're going to tell us all about cryo-EM. One thing that I will request from you is to give specifics on the price tag.
Will do.
Both instrumental setup as well as how much it costs to obtain one single structure if you want to use services. Okay, great. So now we're switching gears, and since Derek was unpleasantly surprised by the cost of this instrument, I want to switch to something which is much more affordable, something that you can acquire for less than $100,000. And the name is quadruple mass filter. A really ironic thing about quadruple mass filters is this. These are the cheapest devices, the easiest to manufacture. However, they are the most difficult ones in terms of explaining how they work mathematically, because the math behind the operation is very, very complex. So I'm not going to pretend that we'll be able to understand everything, but I will try to do as much as possible to get us on the same page. So the instrument itself, or the mass analyzer itself, is just 4 parallel cylindrical rods, as you can see here. So I made one of them transparent, just to make sure you can see what's behind it. But these are identical rods and they're parallel to each other. So I'm not sure how large is my screen, my square on your screen, but this is the actual instrument, so you can get the sense of how large it is. So I'm showing it from one of the ends. So here you see only 3 quadruple rods. One of them is removed here. On this end, you have all 4 of them. Okay, and this is how they arrange. So it really is about 10-15 centimeters long, and each of them is less than 1 centimeter in diameter. So that's the arrangement. So very, very small and very easy to manufacture. So the way it works, you connect electrically 2 opposite rods. So these 2 guys will be connected to each other electrically, and these 2 guys will be connected to each other electrically, right? So essentially you have 2 electrodes here, even though they're presented by, each of them has two rods. And then you apply this potential difference. So it has a DC component and a radio frequency component. All right. And under any set of conditions, there would be ions that would be able to make it through the entire assembly. So if you let them fly in here, they will have very convoluted trajectory, which I was trying to depict here using this wiggly lines. But the important thing is that they would be able to make it through. Okay, and they would reach the detector. Other ions with different MOZ values would not be able to make it through. So they will go through assume unstable trajectory, and they will be thrown out of this region. So why does it happen? For those of you who like math, I will show a couple of expressions. There is no need to memorize them or even focus too much on them, because this is not the point of our discussion. But this expression here, so that shows the distribution of the field. inside the quadrupole assembly. So notice that it doesn't have any Z component, right? So let me remove this. There is no Z component here. It's only X and Y. Okay, so you create an ideal quadrupolar field. And the ion behavior in the quadrupolar field is very complex. So again, those of you who like math and maybe took differential equations class not so long ago, I'll just walk you through or try to get you oriented here. So you introduce the notion of dimensionless time. Essentially, it's a product of real time and the circular frequency of your field, right? And then you have to introduce two parameters, A and Q. And so these are very important. A relates to the DC component of your field, and Q relates to the radio frequency component of your field. So these are the amplitudes of these two components. And the behavior of your ion inside this field will be described by this differential equation. In mathematics, it has its own name. It's called Matthews equation. And so even though it doesn't have analytic solutions, what we can do, and how many of you guys have taken differential equations class? Okay, some of you did, right? So you know that in differential equations, very frequently our goal is not to solve the equation, but to define the region where the trajectories will be stable, right? So that's particularly important in chemical engineering. So Ben, I'm pretty sure you spend a lot of time talking about that. So here we do pretty much the same, but when you took differential equations, I think you focused mostly on hydrodynamic issues, right? So this is electric field, so it's slightly different, but the idea is the same. And so it turns out if you plot the family of solutions, or if you present it in the 2D form, so these are my two parameters that I introduced earlier, my DC and my radio frequency component of the electric field. So the triangle, curved triangle shaded in gray shows the stability region. So all ions whose M over Z values fall within the gray triangle, they are stable. So they will have very different trajectories, but what's common to all of them, they would be able to go through this quadrupolar filter, and I would be able then to detect them using a detector if I put it on the opposite side of the quadrupolar assembly. So now, of course, having this, selecting conditions somewhere here is not really useful for us in terms of mass spec measurements, because it means that in addition, a slight variation in M over Z is not going to change the transferability of my ions, right? So I need to find a way to introduce some discrimination between ions with close M over Z values. And the way we have to do that, we have to go to the very tip of this triangle. So we select the conditions that places at the very tip of the stability region. And so ions that have M over Z values that correspond to the black point here. So these guys would be stable. They would go without any problem through the quadrupole, and I would register them at the other end of the quadrupole assembly. However, a small variation in M over Z would take me either here or there, right? And so that would, now these ions would be thrown off of the quadrupole assembly. So I will not be able to detect that. So now I have the ability to discriminate against ions with slightly different M over Z values. So, and if I keep conditions, so these would be unique U and V values that I would find, so they would help me stay there, right? So I get rid of everything else, but I keep this just ions of this type inside the instrument. If I want to acquire a spectrum, so now I'm interested, I want to see all ions that I have there, but I want to go through them one by one. And so I want to acquire a mass spectrum, which is a plot of ionic intensity as a function of M over Z. What I would have to do, I would have to change these two values in concert, in sync with each other. So I would maintain the ratio constant. And so that would allow me to change the M over Z value of ions that are stable in the quadrupole in that particular region. So this is how I acquire a mass spectrum. So it's called U over E. I'm sorry, I'm going in the wrong direction. U over E scan. Does it make sense? I know I threw a lot of things here without really giving proper explanation, but please let me know if it makes sense, because this is really important, and I would rather spend some extra time instead of just galloping through these things. Ben, does it make sense? Okay, Marissa, you fine with that? Good. Okay, so this is how I acquire mass spectrum, right? This is the brown arrow shown on this diagram. There is another way these devices are operated. And so instead of doing this scan, I can just make the DC component 0. Right, and then if I make DC component 0, then I will be here. And now I maximize the amount of ions that are stable, right? So only ions that have very low M over Z, so ions in this region, would be unstable, right? And so this is another regime. We frequently use quadrupoles, not just standalone instruments, but as ion storage devices, so ion guides. And when you do that, in fact, this assembly that I showed you earlier, it was not taken from a real quadrupole instrument. It's a quadrupole part of the so-called QTOF, quadrupole time of flight, a hybrid instrument where you have a first stage, a quadrupole filter. You can use it as a filter, or you can use it simply as an ion guide. It depends on you, whatever you want to do with that. And so if you want to use it as an ion guide, then you would have to use this regime. So it's called RF only, meaning that your DC voltage is 0, and then everything becomes stable except for ions with very low M over Z, as shown here. So they would fall off this triangle. All right, so this is everything that I said in the bulleted format. The only correction that I should probably make is this. So I said that M over Z values of quadrupole filters, when you operate it to acquire mass spectra, it's limited to 2000 M over Z units. So I would say many modern instruments go beyond that. And so you can, I think the instrument that we have in the mass spec center on the 5th floor, it can go up to 5,000 M over Z units. So, but you cannot really go much further than that. And so that's a huge difference between quadrupoles and time of flight. With time of flight, your M over Z range is unlimited, right? It really depends on how long you're willing to wait for ions at your detector. In the quadrupole mass filter, you are limited very significantly. Okay, so but a big advantage of the quadrupole mass filter is you can easily implement so-called tandem measurements, FSMS measurements. So if you're interested in ion fragmentation, and this is something that I want to at least start today, we'll continue that on Friday. If you want to do tandem measurements, quadrupole mass filter probably offers the easiest, the most affordable means to carry out these measurements. Okay, so these are examples of two very different mass analyzers. And now in the remaining 5 minutes, I want to start at least start a discussion of tandem mass spectrometry. So I want to begin by showing this mass spectrum. This is a MALDI time-of-flight mass spectrum of a relatively short piece of nucleic acid. And so here you see that mostly we have singly charged species, but we also see other charged states as well. And this mass spectrum is acquired very close to the threshold, ionization threshold, which is the level of the laser power at which you just begin to see the signal, okay? And frequently, we want to work very close to the threshold because that allows us to avoid excessive damage of our analyte. So if I were to increase the laser power significantly, I would see very different spectrum. So my intensity would go up very significantly, but at the same time, I would see a lot of other features. So I begin to inflict damage on my analyte. And in this case, it may actually give me some advantages, because if I measure the distances between the adjacent peaks, that would give me the ability to determine the sequence of this particular oligonucleotide. Well, with few exceptions. This technique by itself, when you select conditions that are damaging to the integrity of your analyte molecule, either in the multi-source or you can actually do it with electrospray ionization source as well. It does provide you structural information. It allows you to see abundant structural fragment ions, but you really cannot go very far with that if you have multiple ions in your original mass spectrum, right? Because each of them will give rise to fragments. Then these fragmentation patterns will overlap, and it would be very difficult to make sense of what you see. So frequently, what we do instead of this brute force approach, we use a technique which is called tandem mass spectrometry. And then again, the name is self-explanatory. It pretty much tells you that you put two mass spec devices in sequence, right? And now, instead of this classical team where you do mass analysis and then you separate ions and then immediately after that you detect them, now you isolate ions of M over Z value that you're interested in, and you direct them towards collision cell. And collision cell serves the only purpose, it allows you to fragment your ions. So now you produce fragments, and then you use a second mass analyzer to determine M over Z ratios of your fragments. So you separate them according to M over Z ratios, and only after that you detect them, right? So essentially you have MS1. This stage allows you to select ions of interest, and this would be MS2. So this is the second stage. Now you're looking at the fragments. So this is how it looks in reality. So this is a very old set of data acquired at UMass, but I like it because it shows all three different stages. So we are looking at this rather exotic molecule, and the mass spectrum of the sample does contain a peak ionic signal which shows the correct M over Z value That's the expected MOVZ value for this analyte, but you also have some other things as well, right? And so if you want to produce, if you want to characterize the structure of your molecule based on fragmentation pattern, first thing that you need to do, you want to remove all these things from the mass spectrum, right? And so you can do that in the first stage, let's say in the quadrupole mass filter, we would just select the conditions that would allow us to keep only these ions in the stability region, and everything else will be thrown off the quadrupole mass filter, right? And so then the resulting mass spectrum would look very clean. You have just one type of ions in the mass spectrum. And so after that, you can induce fragmentation. We are going to talk about different ways to do that this coming Friday. So in this particular case, you just induced collisions between molecules of neutral molecules of so-called collision gas. It could be nitrogen, it could be argon or xenon, or there are a variety of options for you. As a result of that, the intensity of your precursor ion goes down considerably. Remember, see here we were in around 2000 absolute intensity. Now we are around 200. So we lost 90% of our ion. So, and these 90% of ionic population was fragmented. And so now we see very abundant fragments, and we know that they all originated from our precursor. Okay, so other impurities that were present in the mass spectrum initially, they had zero contribution to these fragments. And so in this particular case, it doesn't, we can go through all these ions one by one and determine what they are. I just did it here very quickly for the two most abundant ions, fragment ions, but you can assign others as well. And you can imagine that this is an incredibly useful tool when you are dealing with an unknown, right? And so when you have the ability to break it into pieces, that is a very useful tool in terms of trying to understand what the initial structure was. I want to finish today's class by showing Dan's favorite molecule now. This is called lipid A. And I want to emphasize one thing. So the two spectra shown here, at the top you have MS1, and it shows different forms of lipid A as well as some impurities. And here at the bottom we have MS2. And I want to emphasize this again. When you fragment it, you go from 10,000 to 1,000, right? So you lose, in terms of the ionic abundance, you lose about 1 order of magnitude. But let me ask you this question. Which spectrum, which one looks more aesthetically pleasing? Which looks cleaner?
The second one?
It's undeniably this one, right? So we lost 1 order of magnitude in terms of ionic intensity, but the signal to noise, and I think this is what determines the appeal of this spectrum, the signal to noise is much better. And the reason for that is that by using this mass selection, we are removing all these impurities. All these things that you see on the background, this is not electrical noise, this is chemical noise. These are all impurities, right? By mass selecting one particular ion, so this is our precursor, and fragmenting it, you are also eliminating all this chemical noise from the mass spectrum. And even though we apparently lose the intensity, we gain in terms of the signal to noise ratio. All right, so on that note, I want to finish our discussion today. Once again, I will stay here for 10-15 more minutes if you have questions, but those of you who need to go to your next class or have other commitments, please do so. And I will see you all again on Friday.
I just
Bye-bye.
have a quick question about this spectrum. Is this a positive ion, positive mode of this lipid A?